Good morning, AP Calculus. I am not with you today, but I am with you in spirit. So first, just like a normal day, if I were here, I'm going to go ahead and give you a problem of the day. So I'm going to ask that the sub pauses the video, give you a few minutes to complete the problem of the day. Notice it says set up but do not evaluate, so it should only take you a few minutes to do this. Draw a picture. Draw your rectangle, set up the integral, and then when everyone's done, the sub can press play and we will go through it. Okay, so here is what you should have. First of all, you have your picture where with your line and parabola. You then need to draw on your rectangle, recognizing that our rectangle has thickness dx. We have 2 points of intersection, which you find by setting the 2 equations equal. We get 2 and -1 as our points of intersection. So our integral to represent the area is the integral from -1 to 2 of our top function, x plus 2, minus our bottom function, x squared. Okay, so yesterday we went through how to find the area between curves, okay? And some of us were a little annoyed with that example where we had to break it up into 2 integrals, okay? There are those cases, and then there are other cases where we can't find the integral of our area, or we can't set up an integral to represent our area between 2 curves by using x. And so sometimes vertically isn't always the way to go, but that is okay because we have the option of going horizontally. Okay, if we have functions that are easier to work with in terms of y, or if we have an opportunity to set up 1 integral in terms of y as opposed to yesterday 2 integrals in terms of x, we can draw our rectangles in horizontally. Okay, so here's a similar picture to what we saw yesterday, except now we can take these infinitely small rectangles that we're going to add up, and they have thickness dy. So now we can integrate from our lower limit c to our upper limit d of f minus g dy. Okay? Notice how we're still going to take the more positive function minus the less positive function. Okay? So when we're talking about integrating with respect to y for our area, we're going to take our right function minus our left function. Yesterday we were taking top minus bottom, bigger function minus smaller function, essentially. Today we're going to take right minus left if we have vertical bars, horizontal bars that we are adding up. Right? So we're actually going to go back to the example that we did yesterday. Okay? Remember, if at any time I move on too fast, just tell the sub to pause the video, and then they can and we can move on. Okay? When I teach to an empty class, sometimes I go faster than usual because I have nobody here asking me questions or I can't see how fast you're writing. So, here we go. Set up and evaluate the integral representing the area between x equals y squared and y equals x minus 2. All right, this is the problem that we had yesterday, and we had to set up 2 integrals to find the area. Now, if we go back and we draw this picture, so remember x equals y squared is going to be that parabola that opens to the right. Anytime y is squared, we're going to have a parabola opening left or right. And then y equals x minus 2 is going to look like this. Okay. we are finding the area in here. Okay, so yesterday we broke up right here. Broke it up right here because our top function or our bottom function switched right there at x equals 1. Okay. Well, now we want to draw our rectangles horizontally so that we have thickness dy. And now you notice that the function on the right stays consistent. The function on the left, x equals y squared, stays consistent. And so we only have to use one integral to find this area. Okay? So like with any problem, we do need these points of intersection. Okay? You can solve for x and then plug back in to solve for y, or we can just right now solve for y. We know we have to integrate with respect to y, so let's keep it that way. So we have y squared equals, here, x equals y plus 2. We want to be in terms of y when we do this. Okay? So when we have y squared minus y minus 2, when we factor that, we get y minus 2 and y plus 1. So our intersection points are at a positive 2 and a negative 1. So to set up our integral representing the area, we're going to go from negative 1 to 2 of our very right function, y plus 2, minus our very left function, y squared. Sorry, that's one. Okay. Now it is very important that you write that dx or dy so we know what variable you are integrating with respect to. It's not there, you don't get full credit for your integral. Okay. All right, so now this is a fairly easy one to do by hand. Okay. 1/2 y squared plus 2y minus y 1/3 y cubed evaluated from negative 1 to 2. Okay. So if we do this here, okay, you do the calculation with me. You should get 9/2 or 4.5. Is that what we calculated yesterday? It should be, right? Okay. We did this problem 2 different ways. Okay, which way is preferable? Okay, I would argue that this way is preferable because we only have to do 1 integral instead of 2. Okay. So this is a time where we could do either way. All right. In the case of like this weird picture over here, okay, I would say that it's a pretty good possibility that integrating by x would not be possible. It looks Like it would be pretty difficult to break up into top minus bottom and all the different possibilities, okay? This is one that's much simpler in terms of y, okay? This one we could do either way, but definitely much quicker to do in terms of y. All right, let's look at another example. Okay, so you are going to have to get comfortable graphing equations that look like this, okay? We're really good when we have functions in terms of x, but here we have functions in terms of y, so we have to think a little bit inverse, if you will, all right? So x equals negative y squared plus 10. Okay, well that means, all right, if we plug in 0 for y, we have an x-intercept of 10. Okay. And no vertical movement since nothing is attached to the y. And then since the y squared is negative, we know that this is going to open to the left. X equals y minus 2 squared. Since that negative 2 is with the y, that means that's the movement that we are going to have. Okay, it's going to be, since it's inside the function, remember it's going to be backwards. Okay, if you're having trouble visualizing that, then plug something in for x or y to kind of figure out where that movement is supposed to be. Okay, but here is our vertex, and we'll open this way. All right, so we need to find this area right in here. Okay, two parabolas intersecting. Now, this is our parabola, x equals negative y squared plus 10. And this is our parabola, x equals y minus 2, the quantity squared. Okay, you can see that if we draw in a horizontal rectangle with thickness dy, the function on the right is consistent with any rectangle, and the function on the left is consistent with all of those rectangles if we were to draw them. Okay. What we need are these points of intersection. We need to know what those y values are. So we need to take negative y squared plus 10 and set it equal to y minus 2, the quantity squared. Okay. So we have negative y squared plus 10 equals, y squared minus 4y plus 4. All right, we have a quadratic to solve, so let's set it equal to 0. So we have 2y squared minus 4y minus 6 equals 0. Okay. Since we're solving an equation, it is allowed to divide both sides by the same number. So I'm going to go ahead and divide by 2 to make this go a little nicer for me. Okay. So we can factor this to y minus 3 times y plus 1. So we have intersection points of negative 1 and positive 3. Okay, look at our graph. Does that make sense for what we graphed? Okay. So now we need to set up our area. So our area is the integral from negative 1 to 3 of our right function, negative y squared plus 10, minus our left function, y minus 2, the quantity squared, dy. Now, in your homework, you'll do some with a calculator, some without a calculator. I'm going to go ahead and let you punch this into your calculator, but I just want to talk about what we would do if you didn't have your calculator. Okay, because this is possible for us to integrate by hand. But what you would want to do is you would want to FOIL that y minus 2 the quantity squared out and combine like terms. You would need to be careful because you are subtracting it, so that subtraction would have to go to each of the 3 terms when you multiply that out. Okay, but let's go ahead and just practice putting this into our calculator. Now, keep in mind that, yes, we wrote all of this in terms of y, but when you use the Math 9 command, it is okay to use x in your calculator. You just need to type in a variable. It doesn't have to be the same one that's on your paper. I read your paper, but I don't read your calculator, okay? So you can do whatever you need to with your calculator to make it easy for you, okay? So as long as I typed this in correctly, I'm getting 21 1/3. Okay, so, since we had, yesterday's lesson, this one goes very similarly. We're just going horizontally instead of vertically. And so the process is still going to be the same. Just make sure you always, always, always draw a picture so that you can see, which function is on the right versus left, and for yesterday's lesson, top versus bottom. Now, you notice in this picture that I did label my graphs, okay? That would be a good idea, especially here since we have 2 parabolas that are facing each other. Label which one is which so you know which one is on the right versus which one is on the left, okay? All right, so we're going to do a fun example here, kind of a out-of-the-box example, if you will. So just follow along with me. Do the best you can. So I want to know the number b, where y equals some number b divides the region y equals x squared and y equals 4 into 2 equal areas. So this is what we are working with. We have y equals x squared is our nice parabola, and then we have the line y equals 4. And what we want, I'm going to go ahead and erase these so we don't get fixated on any of those values. Okay? What we want is we want to take this area in here, and we want some line y equals b to split that into 2 equal areas. Now, it is not going to be y equals 2. You can see that it is the parabola gets wider as we get further away from 0. And so y equals 2, yes, is halfway between 0 and 4, but it's not going to split that region into 2 equal areas. Okay? So what we're going to need to do is we're going to have to figure out the area from 0 to b and figure out the area from b to 4, and then we want those to be equal. All right? So since we're dealing with y values as far as where we're cutting this off, let's go ahead and use horizontal slices. Okay, so thickness dy. So we're looking at the integral from 0 to b, and we want it to be the same as the integral from b to 4. Now, let's talk about those those rectangles there. Okay, we need a right function and we need a left function. Okay, well, if we write this right function right here, that would be, if we solve for x, okay, that's how we get functions in terms of y, we solve for x. This would be x equals radical y. And then this function on the left, this would be x equals negative radical y. So when we go to set up our area, we have our right function, radical y, minus our left function, negative radical y. And we're going to do that for each region, and what we want by the end is for those two regions to be equal. The region from 0 to b, and then the region from b to 4. Okay. So let's go ahead and rewrite this to make it easier for us to integrate. Radical y plus radical y is 2 radical y. So I'm going to go ahead and write 2y to the 1/2. Okay. Then we're going to go ahead and need to find the antiderivative for each. So we have 2 times, this is y to the 3/2 times 2/3, evaluated from 0 to b. And same thing here, 2 times y to the 3/2 times 2/3, evaluated from b to 4. So we can simplify each side to 4/3 b to the 3/2. Okay? So now let's go ahead and use that fundamental theorem of calculus. We have 4/3 b to the 3/2 minus 4/3 b 0 to the 3/2, okay, which is going to be 0, right? And then we have 4/3 4 to the 3/2 minus 4/3 b to the 3/2. So the left side we can rewrite as 4/3 b to the 3/2. On this right side, 4 to the 3/2. The square root of 4 is 2. Cubed is 8. 8 times 4 is 32. Okay. Then we have b to the 3/2 on both sides of the equation. So I'm going to go ahead and add this negative 4/3 b to the 3/2 to the other side, so that we have 8/3 b to the 3/2. If we divide by 8/3, we're left with 4. So b to the 3/2 equals 4. Flashback to algebra 2. To get rid of a 3/2 power, we need to take the 2/3 power to each side. So our b value is 4 to the 2/3. Okay, now, this is what I would consider more of a challenge problem, okay, but it's always good for us to be exposed to different types of problems, okay? What I want you to focus on is really the first 2 examples that I did, okay? That's what your homework is going to be like. Now, when you do your homework, I do want you to do 26 and 27 without a calculator so that you don't use that integration practice. But then the rest you can do with a calculator. You can use that Math 9 command. Okay? Tomorrow you will have an opportunity to talk to each other about the homework. Obviously, now until the end of class, you are going to work on your homework. You will work together, help each other out. Tomorrow you're going to talk about the homework with each other, get through any issues, and then you will have a worksheet where you can practice deciding when to use dx and when to use dy. All right? So get your gold sheet out. 26 and 27, do not use a calculator. Please do those by hand. And don't waste your time. We'll see you after the weekend.